Welcome back to Foresight Radio, where we dive deep into the technologies shaping our world and explore how they're redefining the way we work, live, and lead. I'm Tom Kalopoulos, and today we're embarking on an exciting and slightly mind-bending journey into the realm of quantum computing. Specifically, we're going to explore Microsoft's claim to have achieved groundbreaking results in quantum computing with their Majorana 1 chip. So let's start with the simple truth. Classical computing, that is binary computers, are approaching their limits. Moore's law, the observation that the density of transistors on a chip doubles roughly every 2 years, has driven decades of rapid progress in computing. Consider that if you have an iPhone 16, there are 16 billion transistors on its bionic chip. But we're hitting a physical limit, a constraint of silicon. Transistors are approaching atomic scale, where subatomic quantum effects disrupt their functionality. Simply put, we can't shrink them much further. That's where quantum computing comes in. Now, if you're new to quantum computing, you might want to listen to the earlier podcast that I had done with IBM's Bob Sudor. Quantum computing doesn't just add more transistors that can process more binary bits of data. It reimagines how computers work. Quantum computers use what are called qubits. And unlike binary bits, which can be in the state of a 1 or a 0, a quantum bit exists in what's called a superposition of both 1 and 0. The best way to understand how quantum computers work is to think of solving a complex maze. Classical or binary computers would approach that problem in much the same way that you or I might, by tracing each path through the maze until finding one that solves the problem. A quantum computer, on the other hand, would be able to simultaneously take all paths through that maze. And we'll come back to exactly what this means in just a bit. But as far as Microsoft's Majorana 1 chip, it's a game changer because it introduces a new class of materials called topoconductors that achieve what's referred to as topological quantum computing. So what's so great about topological quantum computing? Imagine that you're building a house of cards. The structure is incredibly delicate. Any disturbance, even the slightest disturbance, like a gust of wind or an unsteady hand, even the vibrations from walking on the floor can cause the entire thing to collapse. This is exactly the challenge faced by traditional quantum computers. Their qubits are incredibly sensitive to their environment, and even a tiny vibration or a change in temperature can lead to what's called decoherence. That's where the quantum state collapses and the information it holds is lost. Topological computing, on the other hand, takes a completely different approach. Instead of relying on a fragile house of cards, it works more like tying knots in a rope. The information isn't stored in a single delicate element, but rather in the way these knots are woven. Now, I know this sounds obscure, but stick with me. The key is that small disturbances don't untie the knot. You can wiggle the rope a little bit, you can stretch it or change its shape slightly, but as long as the knot remains intact, the information is still there. This approach utilizes exotic particles known as anyons. Majorans, by the way, are a type of anyon. Anyons exist in a two-dimensional space. When these particles are braided, imagine weaving their paths around each other, the specific pattern of braiding can represent and manipulate quantum information. The beauty of this method is that the exact path details aren't as crucial. It's the overall braiding pattern that matters, providing inherent stability to the computations. Now, to be clear, Microsoft is claiming to have harnessed Majorana particles, but there's some controversy in the scientific community about that claim. Nonetheless, Microsoft's announcement points to what could be a significant advancement. After nearly 2 decades of research on Microsoft's part, they've engineered a new material called a topological superconductor. And this material hosts particles known as Majorana fermions. I know we're getting a little obtuse here, but the reality is that quantum computing, by its nature, is relatively obtuse. What's important is that these particles are less prone to errors, and that's critical to our conversation. And it makes them ideal for constructing more reliable qubits. That's always been the challenge, is reliability of the qubit. Recall our house of cards and rope analogy here. The Majorana 1 chip leverages this reliability and allows scaling of quantum computers. And what this means is that while today's quantum computers are limited to a few thousand qubits, Microsoft's approach could allow for up to 1 million or more qubits on a single palm-sized chip. And this would enable quantum computers to tackle complex problems that are currently well beyond the reach of classical computers. When I say well beyond the reach, I'll give you an example. Take the problem of cracking 2048-bit RSA, a key that's used to encrypt data. That would take about 300 trillion years on a classical computer. The universe, by the way, is 13.8 billion years old, so you're starting to get the sense here for how daunting some of these problems are. If we had a fault-tolerant quantum computer with 20 million error-corrected bits, it could do that in about 8 hours. So 8 hours versus 300 trillion years. This isn't an esoteric discussion. It has real-world implications. Some calculations, like simulating complex molecules for drug discovery, would also take billions of years on a classical computer. So quantum computers can be used to solve problems that are rooted in extreme complexity. Many of these problems deal with situations such as biology, where the number of possible paths that you can take to a solution are nearly infinite. Cautious optimism is needed here. Some physicists have expressed skepticism about Microsoft's claims, suggesting that more evidence is needed to conclusively demonstrate the existence of these Majorana particles. But look, we're early into the exploration of quantum computing. What's important is the enormous leap forward that something like what Microsoft is doing can provide for longer-term viability of quantum computing. There's no doubt that further research and verification will be necessary to confirm their viability. However, with players like Microsoft, IBM, Google, NVIDIA, IonQ, and many others investing billions in the development of quantum computing, breakthroughs are absolutely inevitable. Fundamentally, we're on the cusp of an era of accelerated innovation unlike anything we've witnessed before. If you thought AI was transformative, just wait until it's powered by quantum computing. The organizations and the individuals who embrace this shift early, who pay attention to what's going on and find ways that they can build on some of these advances, will be the ones who are shaping the future. That's it for today's episode. If this discussion sparked your curiosity, make sure to subscribe and let's keep the conversation going. Until next time, keep thinking big and pushing the boundaries of what's possible. And as always, stay curious.